Welcome everyone. Now we will look at convolution. First we will look at this for discrete time signals and systems, followed by continuous time signals and systems, which would lead to the convolution integral. For the discrete time signals and systems, we would have convolution sum. A linear system response to a linear combination of inputs is the same as linear combination of the individual responses for a linear system. Now we saw that before. What this means is, if we have a linear system and if we give it xt and yt is the output, if you give this linear system x1t and the output is y1t, and if you give it another input x2t and the output is y2t, if you give a linear combination of these two, like x1t multiplied by a plus x2t multiplied by b, the output should be the same linear combination of the outputs. That means a times y1t plus b times y2t. So that means the addition or superposition of signals results in the superposition or the addition of the outputs. That's a linearity. Then we have the time invariance. Time invariance means that the system is not sensitive to the time origin. So if the input is shifted by some time, like t naught, the output is also correspondingly shifted by the same amount. So in this case, for the same system, if you give x t minus t naught, the same output shape y will be just time delayed by t naught. So depending on the time, the shape does not change. So what this means is, if you give xt minus t naught, the output will not be some different y. Maybe it will not be yt that is different from the earlier y, but the earlier y will be just time shifted in correspondence with this same t naught. So for a linear system, if the system inputs can be decomposed as a linear combination of some basic inputs, that means we have sort of an xt and we decompose it into basic inputs like x1t, x2t, x3t and so on. And the same response is known for each of these basic inputs. Now if we select these basic inputs to be the same signal, perhaps time delayed, then the response can be constructed as the same linear combination of the response to each of these basic inputs. Signals can be decomposed as a linear combination of basic signals in a variety of ways. For example, we can use a Taylor series to decompose a signal. However, in the context of signals and systems, it is important to choose these basic signals in the expression so that some sense the response is easy to compute. What this means is, when you send these basic signals, consider this to be a basic signal that we are inputting, this response is easy to compute. So this is how we select these basic input signals to decompose our original signal xt. For a system that is both linear and time invariant, there are two particularly useful choices of these basic signals. First one is the delayed impulse, and the second one is the complex exponentials. So in this lecture, we develop in detail the representation of both continuous time and discrete time signals as a linear combination of delayed impulses and the consequences for representing linear time invariant systems. The resulting representation is referred to as the convolution. Earlier, we developed in detail the decomposition of signals as a linear combination of complex exponentials, referred to as a Fourier analysis, and the consequences that representation for linear time invariant systems. This consequence we will relook at after we cover convolution. So using convolution, we can express the response of an LTI system as an arbitrary input in terms of the system's response to the unit impulse. So this unit impulse response is very important. What this means is, for a discrete time system, we give it delta n, and the output will be what? which has a special symbol Hn. H is the unit impulse response. For a continuous time system, if we give it delta t, ht would be the impulse response. So this H is a special symbol. An LTI system is completely characterized by its response to a single signal, namely its response to the unit impulse. So that means if ht is known and if the system is linear and time invariant, we fully understand the system. In discrete time, we have the convolution sum. In continuous time, we have the convolution integral. Okay. So once again, the strategy for exploiting linearity and time invariance is decompose the input signal to a linear combination of basic signals. Choose basic signals so that the response is easy to compute. That means for analytical convenience. So if you choose delayed impulses, that leads to convolution. If you do complex exponentials, which leads to Fourier analysis. Okay, so first of all, we will look at the discrete time case. So first of all, we want to express a dt signal as a superposition of weighted delayed impulses. So impulses are there and we delay them, and actually we will multiply these delayed impulses by different weights which are related to the original signal. We can express a dt signal as a linear combination of weighted delayed impulses. If we have a linear system and a signal expressed as above as a linear combination of basic signals, the response would be the same linear combination for the responses for the individual basic signals. Okay, so let's move into the representation of the signal xn as a linear combination of weighted delayed impulses. So let's take this example. It has 5 non-zero samples. So now first let's take this sample x minus 2. So if we only represent that sample, you have to write as x minus 2 delta n plus 2. If you just write x minus 2, what this means is, let's say this is wn, for example. Wn is x minus 2. For any n, the value is x minus 2. X minus 2's value is, I could take it as 1, let's say. So it is always 1. So if you plot that wn, so you will have to plot 1s throughout, right? So we have to place it at n equals minus 2 by multiplying that with n delta n plus 2. Okay, now let's represent this sample like this. X minus 1 is the value or the weight, yeah, and then delta n plus 1 must be there. Next, node times delta n, x1 times delta n minus 1, x2 times delta n minus 2. Then what we do is we sum all these things. So therefore you see this is the sum. Xn equals x minus 2 delta n plus 2, x minus 1 delta n plus 1, and so on. Now we can write this as an expression. Xn equals k goes from minus infinity to infinity xk delta n minus k. So you saw this value is that k that we want. So in this case we have expressed xn as a linear combination. Now this is that linear combination. This is the signal, that basic signal of weighted delayed impulses. Now these are impulses and they are delayed by that particular time k, and they are weighted by these constants xk's, weighted delayed impulses. So these impulses are the basic signals for which the output is easy to compute. All right. Now let's look at how to obtain the convolution sum. So for our system, the input is xn, which we have decomposed as a linear combination of basic signals delta n minus k. Okay, now we consider that system to be only linear, not time invariant yet, only linear. So if the signal is linear, the output would be the same linear combination of the input. Now, in this linear combination, these are these constant weights. Constant weights are these. These are those signals. So, what we say is, now if we input this delta n minus k, we get the output hkn. Yeah, hkn. If you take a particular example, if you take delta n minus 2 as the input, the system will give the output as h. You can see k is equal to 2. This is what we are saying. Because we have so many signals like this, we have to sum all of them to compute the output. Same linear combination, because you can see these constant base xk are right here. So you can see we have applied the linearity property of the system to compute yn here. So what this represents is, what this diagram represents, if we give delta n minus k to the system, the output would be hkn. Now we can apply the time invariance as well. Now, a time invariance means when h naught is the response of the system for an impulse at 0, when this impulse is delayed by k, the response would be same h naught, just delayed. So what we are saying here is, now if we give delta n, we take the output as h naught n. If we delete delta n minus k, the output will be h naught n minus k. The shape of h naught will not change, but it will only be delayed. This is the time invariance property. Then out of laziness, we do not want to write h naught, this subscript, but we would write h naught n as hn. So therefore now if we combine these, we will have yn equals hk. Instead of hkn, we would write hn minus k, which is the convolution sum. So this is an expression that we need to remember. Now to compute each value of yn, that means n equals 3, n equals 4, n equals 5, you can see in this expression n is a constant. We must run an infinite summation. Yeah, k goes from minus infinity to plus infinity. Okay, in summary, the convolution of a sequence xn and hn is given by yn equals k goes from minus infinity to infinity xk hn minus k, which we represent symbolically as yn equals xn convolved by hn. This is the asterisk symbol, which represents convolution. Okay, now let's take an example. Compute yn equals xn convolved by hn for xn and hn as shown in figure 5. This figure 5 is not here. So this is my xn, this is my hn. So if you think about the convolution sum, you can see it is xk and hn minus k that we want. So yn is summation, k goes from minus infinity to infinity, xk hn minus k. So from xn to obtain xk, it's easy, you just replace n by k. But from hn to obtain hn minus k, you have to consider the independent variable as k, and it's minus k. You have to time reverse it and move the signal n minus k by this constant n. Okay, here is that by looking at xn, we write xk, which is easy. By looking at hn, we write hn minus k. Here you can see the independent axis is k. So I have reflected it right from right here to do the time reversal. And then for different values of small n, we have to plot that signal. So this is when n is equal to -2. You can see this origin has gone to -2, here -1, and so on. So what have we got to do? What is our expression? Yn equals summation k goes from -infinity to infinity xk hn minus k. So here is a particular instance of hn minus k for n equals -2. So we have to multiply these two signals. So when you multiply, since there is no overlap between these two, you can see the multiplication is 0. But if you consider n equals -1, there is an overlap over here. So when you multiply, you will get 1. So to show this, I have superimposed xk also over here. So you can see here there is no overlap. Here there is an overlap here. So that means 1 times 1. So you will get 1 here. This one would be 0. So we can see we are computing this for n equals -2. This one is n equals -1. So for the other values of n, for n equals 0, for n equals 1, n equals 2, n equals 3, and so on, we can do this computation. So I have superimposed xk on them. Then you can see here when you multiply 1 times 2 plus 1 times 1, you get 3, and here you get 4, here you get 4 once again, and from this point onward you get 0. So therefore the answer is this, and we can plot it in this fashion. Commas here. Okay, I hope it is clear to you. So let's take another example. Consider an input xn and a unit impulse response hn given by xn equals alpha n un, hn equals un, where alpha is less than 1, maybe like 0.9. Find yn and sketch. So to do that, we can plot xn first to get an understanding. So you can see it's alpha n un. So here alpha is, for example, 0.9. So it is an exponential decay. Since we are multiplying that by un, all the values here are zeros. Then this is un. So hn is un. So but what we want is hn minus k. So you can see for a particular value of n, I have plotted hn minus k with this axis k. So you can see when n is less than 0, no overlap. So when n is greater than or equal to 0, there is overlap. So therefore we can write xk times hn minus k when you multiply these two signals. For values of k from 0 to n, it is alpha k. Otherwise it is 0. This expression is valid. So now thus for n greater than or equal to 0, yn is equal to summation k grows from 0 to n, k grows from 0 to n. You have to multiply these numbers with these, alpha to the power of k, so that summation results in 1 minus alpha n plus 1 divided by 1 minus alpha. It's a power series. And then to express this part using un, you can write it like this. Okay, so next we will look at convolution integral.